Hello, and welcome to the Ubicity, a Pure TOSCA Orchestrator webinar. Just to make sure we all start at the same point, the word TOSCA is an acronym for Topology and Orchestration Specification for Cloud Applications. A couple quick notes before we get started. The session is being recorded. We will send you a link to the recording following the webinar. You are free to ask questions at any point. You can just type those in the Q&A box that you have at the bottom of your screen. We will be taking those after the presentation. Our presenter today is Chris Lowers. He's the CEO of Ubicity and chair of the OASIS TOSCA Technical Committee. And with that, I would like to hand it over to you, Chris. Thank you.
Well, thank you very much, and welcome everyone, and thanks for joining today's webinar. What I'd like to do primarily is give a demo of TOSCA Orchestration in action and focus specifically on the core TOSCA features that enable what I would call pure TOSCA orchestration. And before I do that, let me explain what I mean by pure TOSCA orchestration, and I'll do that in the context of a TOSCA functional architecture. For some of you who've been tracking the TOSCA version 2.0 discussions, this figure may look familiar. It'll be included in the specification of the version 2 document. And it's intended to give users of TOSCA, specifically template designers, a mental model, if you will, of what they can expect or how they can expect their TOSCA service templates to be processed by a TOSCA orchestrator, or more generally, a TOSCA processor. So the expectation is that every technology that implements TOSCA features or the TOSCA language would have a processor component that is shown on the left-hand side here. Oops, wrong button. That TOSCA processor function takes service templates, parses them, validates them, and creates some type of normalized topology template, which would be implementation specific. Those templates would then get fully resolved, which in the context of TOSCA means that all requirements need to be fully resolved, any substitution directives need to be executed, and that ultimately results in a representation of a service topology where you can match that representation with service deployment specific inputs. And that is the representation that ultimately will get processed by an orchestrator in order to create external implementations on some external cloud platform, or more generally on external resources. When we talk about pure TOSCA orchestration, all of these components will be driven by the TOSCA language. There are some implementations where TOSCA will be used just to create the topology representations. But those representations will then be handed off to a third party or a pre-existing orchestrator, such as Kubernetes. We've seen before a presentation by Tal presenting Turandot. Turandot uses Kubernetes as the orchestrator, and that's a perfectly valid approach to use with TOSCA. What I mean with pure TOSCA orchestration is that the orchestration component itself is driven based on TOSCA language features as well. And that's what I will be showing and demonstrating today. And I will show how that can be done without having the orchestration functionality have any awareness of or any built-in knowledge about domain-specific types. The orchestrator can be built without any knowledge about platform-specific implementations, and it can be built without any knowledge about the external resources that are available on top of which services can be orchestrated. What that means, though, is that the orchestrator needs to be made aware of the domain-specific information that is encoded in types. It needs to be made aware of platform-specific implementations, and it needs to be made aware of what the external resources are. And those are the features that are implemented in the Ubicity orchestrator. So let me just give you an idea of how that works. The main feature that we use in Ubicity to make an orchestrator aware about domain-specific deployments is a feature called TOSCA Profiles. Now, this is a, if you recall, the current standard, the version 1.3 of the standard, includes a simple profile, which is primarily focused on infrastructure as a service clouds. What we are enabling in version 2.0 is support for general purpose profiles, where profiles can be created for specific application domains that introduce types that model the entities that are relevant for that type, for that domain. Those profiles and those types can include artifacts that provide implementations for those types. Profiles could potentially also include service templates that could be used as substituting templates for applications in that application domain. All of those can be packaged together in what's called a profile using the normal TOSCA Caesar packaging format, and then onboarded in the orchestrator so that those profiles can be accessed using their well-known profile name by other service templates that may need to use the types defined in that profile. And in Ubicity, we have there's a Ubicity command line tool that's called Ubicity, which has an option to list available profiles, to add profiles using the Caesar file name, to show the profiles in the orchestrator, and to delete profiles if necessary. And I'll just go on and show those in just a second. The other aspect I'm mentioned is that TOSCA is based on service templates that are again packaged in Caesars. The Ubicity paradigm is that we first onboard those service templates based on the Caesar files into a catalog, and then services are instantiated by selecting templates from that catalog based on catalog ID. And similarly to the profile commands, there are Ubicity catalog commands that allow you to create, list, show, and delete profiles. Those service templates obviously will be used to instantiate and to deploy running services. But what's somewhat unique in Ubicity, I believe, is that we use the same service templates to also make the orchestrator aware of the available external resources on top of which services can be deployed. As I said earlier, in a pure TOSCA orchestration paradigm, the orchestrator starts off knowing absolutely nothing. So it has no, ideally, it has no knowledge about the fact that there may be Amazon clouds or Azure clouds or Kubernetes clusters or edge devices available on top of which services can be deployed. So what we do with the Ubicity orchestrator, we make the orchestrator aware of the available resources by using a resource command that instantiates and models external available resources very much in the same way that you would model deployed services. And the advantage of that is that in the inventory that tracks all the services and all the resources, we use exactly the same model for deployed services and the same models for available resources. And in the end, what that means is that from an orchestrator point of view, there really isn't any difference between what was previously there and which was onboarded in the orchestrator versus what was created by the orchestrator. Either way, the representations represent entities out in the external world that are available and that the orchestrator knows about. And then finally, obviously the important aspect of the orchestrator is to then deploy services, and that's done using the Ubicity service command, where again, we instantiate services based on an entity from the catalog. We give it service-specific input values, as I'll show in just a second, and then we can track the status of that deployed service based on what's kept in the orchestrator database, in the orchestrator inventory. So what I'd like to do now is show this in the context of an example service, and the example service I'll use is a Kubernetes cluster that I'll deploy on a cloud service. So let me just demonstrate how this can be done, starting from absolutely no information in the orchestrator. So I have a simple install script that just puts files in the right location and initializes the Ubicity inventory database. So that's effectively all the installation script does. And if I go to my command line tool, I can, as I showed you earlier, I can list the available profiles. When the Ubicity Orchestrator is first created, the only profile that is available is a profile of built-in TOSCA types. And these need to be available so that they can be referenced by properties and attributes and what have you in Ubicity, in TOSCA service templates. And let me just show you what that profile looks like. So these are, as you might recognize, there's the built-in types such as string, integer, float, boolean, and so on. There's no real additional information available, but again, any available TOSCA type will be kept in the Ubicity type catalog, so it can be referenced. And the built-in types are no exception, so they're managed in exactly the same way as custom types that may be onboarded using profiles. Now, as I said, the Ubicity Orchestrator starts with knowing absolutely nothing about available resources. So if I do a Ubicity resource list, that should be completely empty. If I do a catalog list, that should be completely empty. And obviously, since we haven't deployed anything, if I do a service list, that is completely empty as well. So in order to make the orchestrator aware of information that can be used for deploying services, I need to do two things, or three things actually. I need to onboard profiles that have types available that can be used. I need to onboard resources on top of which services can be deployed, and I need to deploy services based on service templates in the catalog. And I have a simple script that will at least onboard those various entities. And I think it's called init. And I'm showing the init script right on the screen right here. So it doesn't do a whole lot. It has, I have a set of predefined Caesar packages with various profiles. I'm onboarding the TOSCA simple profile. The specification has a set of non-normative types in the 1.3 document. I'm onboarding those as well. I've got Ubicity specific types that are in the Ubicity profile. Those will be onboarded. And then I'm in the context of this demo, I'll demo Amazon Cloud, OpenStack Cloud using Rackspace, and I'll use some Kubernetes types as well. So all of these will be onboarded using the Ubicity profile command. And then using those profiles, I'm also onboarding a Caesar package that models available resources. And the resources I'm modeling are the various availability zones on Rackspace and availability zones on Amazon, so that those availability zones can be used by the orchestrator to deploy services. And those are done using the Ubicity resource add command. And when I'll just show you what the output of that is right here. If I show you the Ubicity profile list command now. Now there's a bunch of profiles. Let me just show you one of them. The Kubernetes profile is profile 18. So, and the details here are not that important, but this you'll recognize this is standard. This looks like standard TOSCA. So this is types for, I've got a namespace, config map. There's some various types that are that represent Kubernetes admin tools. There's service account. So these are the types that represent Kubernetes resources, as well as some helper types to deploy admin tools. I also showed you onboarding some resources. So if I do a Ubicity resource list, I've got two sets of resources. One is a Rackspace set of availability zones, and the second is a Amazon availability zone. So let me just show you the Amazon ones. Again, this went by a little fast, but it shows you availability zones, which has a name and location. There's additional information that could be kept if necessary. The idea is that these resource representations will have all the information that is necessary for an orchestrator to access and use those resources. This example keeps it very simple. It just uses the name of the availability zone and some information about the location. But you get the idea that this is how resources can be accessed by the orchestrator. Now, at this point, I still don't have anything in my, I have in my service catalog, I have the resource representations. If I show you the catalog, I've got the resource representations for Amazon and for Rackspace, and as you'll see, this is not a very user-friendly name. One of the challenges with TOSCA is it doesn't really introduce names for service templates. One could use metadata for this, but this specific template doesn't have metadata, so it just shows an internal URL for what the service templates are accessed by. If I want to deploy a service, and specifically the Kubernetes cluster service I talked about, I need to first onboard the service template for that Kubernetes cluster, and I'll then instantiate it based on the ID of that onboarded service template in the catalog. And let me just show you how that works. Let me go to my my script terminal here. So I've got a script here that'll run this whole demo takes about 15 minutes to fully deploy, so I'll just get it started, and then I'll take you through what the service will actually will try to do. So let me just give you a quick idea of what that run script looks like. So what's at the beginning here is not important, but what I'm doing, I'm zipping up the archive into a Caesar file, and then I'm onboarding it using this Ubicity catalog add command. I'm onboarding the Kubernetes cluster Caesar file into the Ubicity service catalog. I'm capturing the service ID that is assigned, and then I'm using that service ID to instantiate a running service based on a set of inputs that will be retrieved from a file that is specified as well using the command line interface. And the inputs, again, they're not that important, but let me just show you what they look like. Oops, if I can find the right location here. So what I'm doing here is I'm giving the cluster a name. I'm saying that the cloud provider is OpenStack, which I'll show you in a minute how that results in the service being deployed on Rackspace. I'm deploying in Sydney, which may sound a little strange, but we had a bit of a challenge this weekend. Rackspace updated some of the software on their Zen hypervisors. In the process, unfortunately broke some things. They've rolled out a fix, but they started in Sydney first and then rolling out to the rest of the world. So I didn't want to risk changing after I verified that it was working in Sydney. I didn't want to risk moving it anywhere else, so I'm just keeping the demo in Sydney for the time being. So this is now off and running. Again, there's at this point, if you wanted to look in the detail of the logs, it's just instantiating a VM on Rackspace, and those things could take a couple minutes. So I'll let that sit and just go back to the presentation and show you what the service looks like that I'm trying to deploy. And this will highlight some of the TOSCA features that I want to illustrate that are a key part of Ubicity. So the service template I'm trying to deploy is actually quite high level and quite abstract. It's fairly simple. It has 3 nodes. It has a master node, which represents a Kubernetes master node. It has worker nodes, and I'll show you there's an ability in Ubicity to instantiate multiple nodes from the same node template. In the example, I'm instantiating one, but using this service template, there would be a possibility to instantiate more than one. And then I'm also modeling the network, the host network that will be used by the cluster to interconnect the various nodes, specifically the master node and the worker nodes. And I apologize, I'm going to go back and forth a bit between the slides and the YAML in my VM here. So let me just give you an idea of what this service template looks like. It's called main, I believe. So let me just show you some relevant parts of the template. So in the template, as I said, there's only 3 node templates. There's a cluster master, which is of type Kubernetes master. There is a cluster worker, which is of type Kubernetes worker, and there is a cluster network, which is of type Kubernetes network. And these are defined in my Kubernetes profile, which I'm importing using the well-known profile ID. Now, again, this may seem a little odd, and it is, because this is a TOSCA version 2.0 feature that we have backported to version 1.3 by hijacking the namespace key name that is part of the version 3 specification. So this is not entirely valid TOSCA, but it allows us to implement the forward-looking feature in a way that is at least somewhat standard using the TOSCA version 1.3 standard. The other aspect that may seem a little odd is that I have the ability in this template to instantiate more than one cluster worker node from the same node template. And this is an extension that is actively being discussed in the context of TOSCA version 2.0. I believe there's lots of value in supporting something like this, but there's all kinds of edge cases that need to be clearly worked through and make sure that we're not overly complicating the spec. But to give an idea of what the feature looks like, just like in relationship templates or relationship definitions, TOSCA has the ability to specify using an occurrences keyword how many instances of a relationship or of a requirement you will create. What we're suggesting here is that same approach could also be used to specify how many instances of a node template can be created using the same occurrences keyword. And in this scenario, I'm using the get input value to allow service operators at deployment time to specify how many node instances of this node template will be created. And that input is defined right here. So this is defined in the inputs section of the node template, and that will be picked up at deployment time. And then again, using this extension, if the number of workers input is greater than 1, we'll create multiple instances of this node instance, of the worker node instance. They'll be differentiated internally using a new reserved keyword that we were suggesting. Again, just to be very clear, this is not standard TOSCA in version 1.3. These are extensions that we have implemented and that we're proposing for 2.0. But each instance would have an occur index that uniquely identifies the index, the specific instance created from the template. And we'll use it in this scenario, for example, to create a unique name property for each of these nodes. So just wanted to highlight how simple this template is, how we use profiles to access predefined types that were onboarded in the orchestrator, and then also give an idea, a preview of a feature that we think might be very helpful, which is the ability to instantiate multiple node instances from the same node template. And by the way, just showing the deployment is still ongoing, trying to instantiate the various instances on rack space in this scenario. So let me just see if we can get an idea here. So this the master node is fully deployed. the software is now, or the orchestrator is installing the various pieces of software on that master node. And when that's done, it'll move on to the worker nodes. Now, I mentioned that the service template was very high level and very abstract. So in order to turn this into something real without the orchestrator knowing much of anything about Kubernetes specifically, or about details of what these master and worker nodes look like, we need to give the orchestrator information about how to actually implement these nodes. And we do that using a feature called substitution mapping in TOSCA. And what substitution mapping lets you do is it lets you implement a node of a specific type using an entirely new service or an entirely different service topology that in a declarative way provides an implementation for nodes of that type. So in this scenario, what I'm doing is I'm using the example of the Kubernetes master node, which in the abstract template is just one very simple node template. But what I'm also showing is that in my catalog, when I onboarded the package for the Kubernetes cluster, that package included additional service templates, specifically a service template for a master node that gives you the details of what's inside the master node. And again, this is fairly simple for the purposes of demonstration, but in this template, what we're showing is that at the bottom here on the left-hand side, we start with a compute node, on top of which we're then deploying Docker. We're using Docker as the container runtime for this demo. Then we're installing the Kubernetes master software after Docker has been installed. And then for networking, I'm installing Calico for this demo. The templates, you could design different templates for different container runtimes or different networking stacks or what have you. But this is what's being used in the context of our demonstration today. And then using the substitution mapping feature, we're telling the orchestrator how the various requirements of the nodes of type Kubernetes master, how those requirements map to requirements that are available in node templates of the substituting template. Specifically in the master template, I didn't highlight this in detail, but we have a requirement for a linkable capability, which was called cluster network. In the substitution mapping of the master node service template, I'll show you in a second, but that maps to the link requirement of the compute node on which the software is being installed. Similarly, if we have, there's a master capability that is used by worker nodes to join the cluster, that capability is exposed by all types of, or all nodes of type master, and that is mapped using substitution mapping to a equivalent capability exposed by the Kubernetes master software in the master service template. And let me just go to the details of what that looks like. So again, this is the abstract service template that I started with. Now let me go to the substituting templates and specifically the master service template. And as I showed in the diagram, this has a couple more node templates. Starting at the back here, we have a master host, which is a compute node, which is, by the way, derived from the TOSCA simple profile compute with some minor extensions. The extension we added is that in the Ubicity implementation, compute nodes actually have a requirement to be run on something. We assume that nothing can be created out of thin air. So everything has requirements for resources on which things can be instantiated, and that's what the resources are for that we onboarded into the orchestrator. But that is really the main extension of the Ubicity compute node versus the simple profile compute node. And then on top of that, we installed Docker software, which is this node template right here. We installed Kubernetes software, specifically the Kubernetes master. There's an admin node, and that's done for initializing the credentials and that can be used by kube control later on, so that those credentials can be available for administrators that want to administer the cluster. And then finally, there's the Calico networking stack that's installed once everything else is done. So that's the template, and that template is linked using the substitution mapping section to master nodes of the type abstract master, which was defined in the Kubernetes profile I onboarded earlier. And if you're familiar with substitution mapping in TOSCA, you'll see that we have so the node type advertises the type for which this template can act as a substitution. That is the core mechanism to advertise substitution mapping or availability to be used for substitution mapping. Then the next section maps properties of the abstract node to inputs of the substituting template. For example, the abstract node has a cluster name property that is mapped to the cluster name input right here of this substituting template. And again, normally you'd have a whole bunch of configuration parameters. For purposes of keeping it simple, there's only a small number here, but you get the idea. And then similarly, we map the master capability of the abstract node to the master capability of the Kubernetes master node in this template. And we map requirements, specifically the cluster network requirement, onto the link requirement of the master hosts, which is the compute node in this template. And by the way, this guard template is there to to make security groups available, which I won't go into today, but this is related to access control and security groups. And so this whole thing is now using substitution mapping is linked to the abstract node and can be used by the orchestrator to implement abstract nodes using a more specific service template. Now that's only that gets us a long part of the way there, but what that doesn't do is it actually doesn't tell us how to implement specifically the master compute node. In order to do that, we use a second level of substitution mapping. And TOSCA substitution mapping can be used recursively, and there's no limitation as to how many levels of depth you can go into. Whereas in the substitution mapping I just showed you, we use substitution mapping to turn abstract nodes into concrete implementations. What this slide shows you, it shows you a second way in which substitution mapping can be used. It can be used to have general purpose nodes, such as a compute node, and have those general purpose nodes be translated or substituted by platform-specific implementations. And in the context of the demo here, I'll show how that compute node can be implemented using a set of OpenStack resources. You could also use Amazon resources or Azure or what have you, but it's the ability to take that general purpose node based on a general purpose node type, specifically the compute node type, and turn that into a specific implementation that allows portable templates that can be created and be deployed on a variety of cloud infrastructures and have the decision of which specific cloud to deploy it on, have that be made at deployment time by the operator as opposed to by the service designer at design time. And let me just try to go back and show you that as well. So this is, again, this is the service template that implements the master node. I have a directive here that says substitute, which again means that this node is abstract or needs to be substituted. And I'll look in the catalog for substitution candidates. So I've let's see which I've got. Let me show you specifically the one that we use for Rackspace. So this again advertises substitution mapping. This is a service template that implements an OpenStack compute node. And there's not a one-to-one mapping. In fact, we have in real implementations, you might have a whole bunch more nodes, but for purposes of the demo, we split off the host from the port that we used to connect to the cluster network that was previously defined as well. So it shows how a single node of type compute can be implemented using multiple node templates. The compute host itself is now implemented using an OpenStack compute, where OS is the namespace prefix for the OpenStack profile. The OpenStack compute host has specific implementation scripts for deploying on OpenStack. It has a bunch of other properties that might be relevant for OpenStack that may not be relevant for other clouds and what have you. And we use the OpenStack port to connect to the network, as I suggested earlier. And then we have the substitution mapping section that maps the properties to the templates inputs, and it maps requirements, specifically the link requirement of the abstract compute node to the corresponding link requirement of the compute port. And this is the mechanism that we use in Ubicity to say that, look, at deployment time, use the OpenStack implementation rather than other implementations that may be available. So then the final question is, well, how does the orchestrator then decide at deployment time which one to use? And that is then using property values that ultimately get propagated onto node filters and substitution filters. Again, if you're familiar with TOSCA, when you fulfill requirements, service designers have the ability to specify node filters that narrow down, or that act as a query, if you will, that narrow down the available candidates that can be used for fulfilling requirements. Similarly, when you advertise substitution mapping, service designers have an ability when they create their substituting templates to define filters that specify more narrowly what the values are of the properties of the abstract node that make it possible for your substituting template to be a valid candidate. And I'll show you both the substitution filter and the node filter that might give you an idea as to how that is being used. So in this scenario, in the substitution section, this is the compute node for OpenStack. I'm advertising here a substitution filter that says, look, I'm only a valid candidate for substitution when the cloud provider has the value of OpenStack. And by the way, the cloud provider comes from the abstract compute node that was in the master node template, which I think I still have right here. So the cloud provider is a property of my abstract node, and it itself comes from an input value that is all the way from the top level template, where it's provided as an input by the operator that deploys the service. So you can use these property values to drive selection of substituting templates. Similarly, we also have a region name, which is the availability zone in which we deploy. That is used in my node filter to specify when I go look up which availability zones do I use for deploying my service. I use the node filter with values based on the region name input to select the appropriate availability zone. And that's how I made sure not only that I deploy on OpenStack, but that I use the Sydney availability zone, or the Sydney region that I wanted to use to avoid problems with some of the other zones. So hopefully this gives you an idea as to how TOSCA can, or how pure TOSCA Orchestrator can use features like substitution mapping to implement abstract nodes, substitution mapping to have platform-specific implementations, and they have requirement fulfillment to make sure that we place things on the appropriate resources, and do that all in a way that is completely transparent to the orchestrator. The orchestrator ultimately just becomes a runtime that only knows how to process the TOSCA language. Everything else is entered into the TOSCA using resource, service, catalog, and profile constructs. Now, in the meantime, this service finished here. So let me just, there should be two nodes created, one for the master node and one for the worker nodes. Let me see if the pods got up and running. So they're all up and running now. So this is now a working cluster on top of which I can deploy a service, which I'll do for demonstration purposes. What I want to try to demonstrate something useful. So what I'd like to do is show you how this cluster can be used to deploy ORAN related services. For those of you familiar with 5G and open radio access network, ORAN is sort of an open source or community effort to create a standard software for open radio access network deployments that can be used with 5G. There's a variety of software components that are being developed by the ORAN community. Most of them are deployed on Kubernetes clusters, and I'll show you how some of the controllers that are part of ORAN can be deployed. But ORAN, there's actually quite a bit of excitement in the community. Dish Network, one of the big providers in the US, is all in on 5G and ORAN. They've made an announcement that they're partnering with Amazon as their cloud on which they would like to deploy the ORAN components. Now, I just showed you an OpenStack deployment in Sydney, which is not very useful for this ORAN deployment. If I wanted to convince Dish Network that they should use TOSCA as the mechanism for deploying their ORAN components. So what I'd like to do is move my cluster first and put it on Amazon instead before I'll do that deployment. And that is done using a Ubicity service update command. So I don't just use Ubicity to deploy services. I also use Ubicity to modify running services. And when we modify a running service, the paradigm is that the configurable parameters that were set in order to create the service in the first place are the service inputs. So it only makes sense then when you change a service that the mechanism for doing that is to provide new or different input values. And that's what we do in the context of the Ubicity service update command. So let me give you an idea as to how that may work. So what I showed you earlier is a set of input values specifically for OpenStack. So we have a cloud provider, OpenStack, and region name Sydney. I have similar values for Amazon, where the cloud provider is AWS, and the region that I might use is US West here in California. So let me just give you an idea as to what that would look like. So I do Ubicity. Let me first show you the services that are currently running. By the way, what may be interesting here is that in my service inventory, I'm not just keeping the top level abstract service template, but I'm also keeping the substituting templates that reference the abstract service template. For example, let me just give you detail about let me use the cluster worker here, which is number 7. So we have a cluster worker service template, and at the top here, you'll see that it says that it's a substitution for a worker node in the abstract service template, so that the inventory database keeps the relationships between the substituting templates and the templates for which they are substitution. But let me just show you what the service update would look like. So I'm updating my service 3, which was the Kubernetes service, and I'm using a new set of input values, which I just showed you are in the Kubernetes inputs AWS. So again, this will go slightly faster because it doesn't have to go halfway around the world. And I think instantiating services on Amazon is perhaps a little bit faster than on OpenStack as well. So this thing will now go and move and modify the cluster. Now the modification here is not necessarily all that interesting because modification, as I said in this slide here, can mean a couple different things. Ideally, it may just be a reconfiguration of an external resource. So you apply new configuration values, keep everything running. That is the ideal case. But in many cases, that's not necessarily possible. If you apply reconfiguration, that reconfiguration may actually result in having that entity be deleted and have to be recreated. And that's what in this Kubernetes cluster master, that's actually what's going on. In the Kubernetes cluster, we're tearing down the VMs that run the master and the worker nodes on Rackspace, and we're recreating them on an Amazon cloud. So there's not a whole lot to reconfigure. It really is a teardown and a recreation. And again, the orchestrator figures this out automatically based on the topology graph and the available operations for modification and what have you. So it goes through this whole planning stage. The planning stage, by the way, also includes double checking if substitution mappings are still valid, because I showed you earlier that there are substitution filters that say whether a substitution is valid for a specific type. For a specific node of a specific type based on the values of the properties of that node. If those property values change because I applied new inputs, that substitution may no longer be valid and the substitution will have to get redone. So the orchestrator does that. Similarly, with requirement fulfillment, if I found a resource in my inventory to fulfill a requirement, if the node filter for that requirement is no longer valid, then that resource is no longer a valid option. And by the way, that's what I'm using to move to different availability zones. So the orchestrator goes through this whole replanning stage to figure out what to keep, what to delete, what to recreate, what to reconfigure, and then it executes an automatically created workflow to actually affect those changes out in the external world. And that is going on in my deployment right here. So now I'm not taken the time to go through the details of the log files here, but what first happened is there was a deletion of the VMs on Rackspace. There's a recreation. The master node has been created. The Docker, I think, has been installed. Now it's installing the Kubernetes software. Let me just give you a, I neglected to show you earlier, there was an OpenStack VM that is no longer there, so that the VM was successfully deleted. Instead, what I have now is a set of instances being deployed on OpenStack. So again, this is the first one here on Amazon in my US West region. It's in the process of installing software on the master node, and when that's done, it'll move on to the worker node. I think this should finish here in the next couple of minutes, so hopefully we won't run out of time. But what I'd like to do, just once this cluster is up and running, what I'd like to do is then deploy a piece of the OpenRAN software. Specifically, I'll just for those of you familiar with OpenRAN, this is the sort of the high-level abstract architecture of what an OpenRAN deployment looks like. It has a management component, the SMO, which is at least for now based on ONAP. There's a control plane that is implemented using what's called radio intelligent controllers. There's a real-time component and there's a non-real-time component. Those controllers manage the data plane, which consists of the control units, the data units, and the radio units. And then there's unique to O-RAN and to 5G, the ability for service providers to deploy applications for service-specific features and functionality. Those are called XApps and RApps. And what I'm suggesting is that O-RAN could actually benefit from using TOSCA as the single technology for deploying all of this. I think right now there's a mix of a variety of technologies, including Kubernetes, some technologies for deploying the infrastructure. What I'm suggesting is that you can use TOSCA to not only deploy the services themselves, but you can use TOSCA to deploy the infrastructure, specifically the Kubernetes clusters, not just in the cloud, but also on edge devices. You can deploy the control plane, the data plane, the XApps. Ideally, you could do all of that using the same TOSCA technology and have a very consistent, very integrated view of how this all hangs together. Anyway, that's my soapbox personal opinion, but just let me give you an idea of what we will deploy using TOSCA on top of this Kubernetes cluster when it's all done. So what I have, again, for demo purposes here is a TOSCA template that is, as of right now, very straightforward. It actually uses it, so it is a template that will deploy the non-real-time RIC. And so there's a RIC node template here that for now uses a node type that I call Helm app or Helm application. And as the name suggests, all it does is it takes a component that's packaged using Helm and it deploys that on the Kubernetes cluster. Now, that in itself is fairly simple. I think if we were to do this correctly and picking up on the webinar that Tal did way back in when we first started this series, I think TOSCA is a much better alternative than Helm for doing these types of deployments. So ideally, we would untangle the Helm chart and replace it with TOSCA, but that's a work in progress. But in addition to using Helm, there's some infrastructure on the cluster side that needs to get done. I'm installing Helm using a Helm node type so that my orchestrator has the Helm available for deployment. This specific RIC implementation or the O-RAN implementation uses Helm version 2, which still uses Tiller. So I'm deploying Tiller into my cluster. I need to make sure that Tiller has the right permissions using role bindings. I'm using specific namespaces in which to deploy the service. So all of that is done using TOSCA nodes that represent the Kubernetes resources that will be used for this deployment. Now, in the meantime, this finished. So let me just show you the nodes. These are now nodes that have been moved to Amazon. Let me just go to the Amazon console real quick. So we now have the both of the nodes right here. And I think we're almost out of time, so I'll just go very quick here. I think the whole cluster should be running. So what I'll do now is I'll go to my ORAN service. And I think I've got a run command, which what this will do is very similar to the run command I showed you earlier. It'll package the RIC service template using in the Caesar format. It'll onboard that Caesar into the Kubernetes, into the Ubicity catalog. It'll then create a service or instantiate a service from that catalog using specific input values, and it'll do that to the Kubernetes cluster that I just moved from Sydney on OpenStack to Amazon's California region here. This will actually not take that long. It's in the process of installing Helm and configuring Tiller, which is the thing that takes the most in this template. But this will terminate here in just a minute or so. But hopefully that'll give you an idea of what can be done. We have similar templates that we did. By the way, this was done in conjunction with a partner company called Customer Care here in California, who are very much focused on using TOSCA for ORAN, and so these templates were designed in conjunction with our partner. Let me see. This now finished here. Let me. So what you'll see here is a couple of things different than before. You'll see the Tiller pod here that was deployed as part of the service template, and Tiller was then used to deploy the services in the non-real-time RIC namespace. I'm running out of time, and this is not intended to be a ORAN demo, but hopefully you'll get the idea of how TOSCA can be used not just for deploying infrastructure, for configuring software in that infrastructure, but as a general purpose technology that can be used across the whole stack, from deploying infrastructure to deploying sophisticated services such as ORAN, and having the benefit of having all of it tied together in a single technology that gives you single view of whatever is available. So hopefully we'll, as we make progress, have an opportunity to get into a whole lot more detail about this. But hopefully this will give you an idea, and that concludes today's presentation. So thank you very much for sticking through this.
Great job, Chris. Thank you so much. We do have a couple questions. We've got a few more minutes. The first one is, how do you handle past vendor-specific inputs via substitution mapping?
That's a very good question. The way the TOSCA currently works and the way the Ubicity implementation works is that all those inputs come from the top-level abstract template, and then they get propagated by mapping properties to inputs of a substituting template, and you can do that recursively. And that works in most cases, but in some cases, you're right, there may be vendor-specific inputs that are not relevant to the top-level input, and they need to get retrieved from somewhere. And there's and by the way, those vendor-specific inputs typically tend to be the same. They could tend to be the same for all deployments. For example, if I have an input that tells me, well, what flavor of Linux do I deploy? Do I deploy Ubuntu or Red Hat? Typically, you're an Ubuntu shop or a Red Hat shop, so those will be the same. So those types of things are actually better provided using some sort of policy. So one of the things we haven't spent a whole lot of time in the TOSCA TC, but there might be an opportunity to have additional mechanisms for specifying where an orchestrator should retrieve input values from, so that we can have these policy-based or general purpose inputs that could be used by lower levels in the substitution mapping, where it doesn't make a whole lot of sense to get them from the top level. So it's a very good question. It's an issue that we're dealing with. and it may require some extensions to introduce more policy-based support, which I think is the right way of handling that.
Okay, the next question. What does the orchestrator do when there are multiple nodes matching the node filter criteria? And the second part of that question is it random selection or error?
No, and that's implementation specific. What Ubicity currently does is it just, if there's a list of valid candidates, the assumption is that any and all of them are valid, and they'll just pick the first one. But you can implement any mechanism. Again, this can be made to be more sophisticated over time, but that is very much implementation specific and not driven by the TOSCA standard. But today we just pick the first available, and as we get more experience, these algorithms, I'm sure, will get more sophisticated as we go along. But it will not result in an error. Having more than one option is a good thing, not an error.
Okay, great. So are there plans to open source Ubicity or parts of Ubicity?
It's something we've thought about, and if the challenge is we're a very small company, and usually the challenge with open source for small companies is the business model. So if anybody has ideas of how small companies can benefit from open source, I'm all ears. Please reach out to me. But the challenge is around the business model.
Okay, that makes sense. Okay, are the various shown profiles available somewhere?
No, they're work in progress. Again, this is there is a in the context of OASIS TOSCA, we have a repository, a GitHub repository, where we keep community contributed profiles and community provided service templates. So we might contribute some of those to that repository, but as of right now, they're work in progress. Some of them, as I said, we've created for partners of ours, and as a result, not really available for open sourcing. But it's something that as we get further along, we will consider, and they will end up. If we do, they'll end up on the OASIS TOSCA GitHub repository. But as of right now, they're not open source.
Okay, I think we have time for one more. Chris, this is an excellent presentation. That's part of the question, which is wonderful. Thank you. This concept of service deployment is not so well known in TOSCA, but I'm worried about post-deployment considerations. How does TOSCA capture post-deployment changes in service orchestration?
Well, hopefully the example I gave you at the end of updating a running service gives you at least a flavor of what can be done using TOSCA. Using the TOSCA paradigm, the expectation is that an orchestrator that implements day two management of services, meaning support for ongoing management and changes to a running service, that orchestrator will keep a representation of that running service on which you can then operate to make changes. You can use those the orchestrator functionality to redo substitutions, as I said, to redo requirement fulfillment. So all of those features that were used initially for deployment can also be used for day two management. What I didn't show, there's actually a whole set of patterns that could be relevant for service assurance based on marrying a monitoring node, for example, with a running service component node, and have that monitoring information drive notifications that could result in closed loop automation. Again, those are not necessarily part of the TOSCA standard, but could be adopted as best practices or patterns that can be fleshed out to illustrate better how the language, the TOSCA language, can be used not just for initial deployment, but also for day two management. And I think those types of things will get, as I said, they'll get expressed using best practices and using patterns as opposed to language features, because I think the language features are mostly there to support that functionality already. Any other questions?
Sorry, I was chatting away on mute. So I want to remind everybody that this is a webinar that's part of a series, and I will follow up with a link to this series. We have another one coming up in 3 weeks.
4 weeks likely, right? The end of the last Wednesday of the month. So the next one will be
There
the
we
last
go.
Wednesday of.
There we go. Time is flying,
yeah.
right? Okay, so we'll have this recorded. I'll follow up with that as well. If we did not get to your questions, we will follow up after the webinar. And thank you so much, Chris, and thank you so much, everybody, for attending our webinar.
Thank you.
Have a wonderful afternoon.
Bye.
Bye.